Hello, welcome to CSC7013, Advanced Math for Computer Scientists. This is Brady Chen. This is Part C of Module 9, Introduction to Number Theory. Now, in Part C of Module 9, we're going to actually first introduce the concept of prime numbers. And then we're going to actually talk about Fermat's theorem and Euler's theorem. And then we're going to define the Euler's totient function. Normally we use phi of n, where n is any positive integer. And then we're going to introduce one of the most important algorithms to test the primarity of an integer. And that algorithm is called Miller-Rabin. So the concept of prime numbers is very simple. Prime numbers only have divisors of 1 and itself. So if we want to show that an integer is a prime number, then all we need to show is that this number has only 1 or itself as a divisor. So in another word, so if a number is a prime number, then it cannot be written as a product of other smaller number. So it can only write as a product of 1 and itself. Okay. So prime numbers are central to number theory. Now, even in the elementary school, we know that any integer can be factored. You can factorize any integer, right? And we can always factor an integer in the form of the product of other numbers. So we can write a as p1 to the power a1, okay, times p2 to the power a2, and times p3 to the power a3, and all the way you can just time up to pt to the power at. Now each number p1, p2, and pt is called the basis. Okay, so that means p1 is a prime number, p2 is a prime number, and pt is a prime number. If p1 is not a prime number, you can factor p1 even further, right? So, and also we can always organize the base number p1, p2, and the pt in a way that the p1 is the smallest and the pt is the largest. Okay, that's called fundamental theorem of arithmetic. Now let's take a look at an example. Let's say I assume that I pick a number a, which is 144. So first thing we need to do is we try to factor the number a, right? So 144 is an even number, so we can always find a 1 factor 2. And then the second part is 72, right? And the 72 is still an even number, so we can continue to factor it. So 2 times 2, and we have 36, right? Now 36 is also even number, so you can factor 36 even further. We can take a 2, factor 2 out, and then it's 18. Then we continue to do this. 2 times 2 times 2 times 2 times 9, right? So 2 times 2 times 2 times 2 times 3 times 3. So we can combine this together. This becomes 2 to the 4th, the power 4, times 3 times 3, that's 3 square. So we can write a as the product of 2 to the 4 times 3 to the 2. So in that case, the t is 2, right? The number t is 2. And the p1 is 2, p2 is 3, and a1 is 4, a2 is 2, right? And this is unique, okay, if we organize in an increasing order for the base numbers. Now, even though the prime numbers are very easy to understand, but in number theory, prime numbers is also very difficult to study. For number one, now if we try to study how the prime numbers are distributed, it's not easy. Now let's take a look at this table. It's a prime numbers under 2000. So we try to find the certain pattern, but we can't. For example, so the number of prime numbers between 1 and 100, so in here, in the columns here, and we find out there are 25 prime numbers between 1 and 100. So that's almost 1/4 of the total numbers between 1 and 100. Now, so the number of prime numbers between 100 and 200 is, let's see, okay, so that's 21. Okay, so the number of prime numbers between 200 and 300, it's even actually 5 numbers less. So that's 16 numbers. So the prime numbers are not evenly distributed. So that's the reason why it's so difficult to study them. So for example, if I give you certain range of integers, like between 4 billion and 7 billions, how many prime numbers between 4 billion and 7 billions? It's very difficult to tell. So even though it's easy to test whether a number is a prime number or not, right? So that's very interesting. So that's why the number theory is the easiest topic to understand, but most difficult to study. So one of the important theory in number theory is Fermat's theorem. Now the Fermat's theory itself is very simple to understand. So if P is a prime number and A is a positive integer not divisible by P, and then A to the P minus 1 and the 1 are congruent modulo P. So in another word, that means A to the P minus 1 mod P is 1. So that's equivalent statement. Now, the Fermat theorem has an alternative form. So if P is a prime number, A is a positive integer. Now in this case, it doesn't have to be not divisible by P, right? A is any integer. And then A to the P equals A mod P. So that means A to the P and A are congruent modulo P. So in another word, so A to the P mod P is A. Now, the proof of Fermat theorem is not easy, but we can certainly verify, right? We can pick any number P and A which satisfy the condition, and then we can show that A to the P minus 1 is congruent to 1 mod P. Okay, now let's pick any numbers. Let's say P is a prime, so I pick a P equals 5. And A is a positive integer not divisible by P. So let's say A equals, I can pick N equals 9. So 9 is not divisible by N, by 5, right? So then based on the Fermat theorem, we can show that A to the P minus 1 mod P is 1. So in another word, we can substitute A with 9, replace P with 5. We can show that 9 to the 5 minus 1 mod P, which is 5, is actually 1. Can we actually show this? Let's do this. So so 9 to the 5 minus 1 is 9 to the 4 mod phi. How can I actually calculate this? We can use the property of a modular operation, right? So we can do this. So 9 to the 4 mod phi, we can write this as 9 mod phi to the 4 mod phi, right? 9 mod phi is 4. So that's 4 to the 4 mod phi. Okay. And then 4 to the 4, we can write as 16 squared, right? Mod phi. And use the property of the mod operation. So it is the same as 16 mod phi square mod phi, right? 16 mod phi is 16 divided by 5, so the remainder is 1. So 1 square mod phi. So it is a 1. Yes, this is a 1. So we verify that for a particular prime number p and a particular prime number a, p is 5, a is 9, then we verify the Fermat's theorem is true. We can test the alternative form, and it's also true. Another concept in number theory we're going to introduce is Eulers totient function. Eulers totient function. Now we use phi of n for any integer n. So now what's the definition? The definition for Eulers totient function phi of n is defined as the number of positive integer less than n and relatively prime to n. So in other words, what is the Eulers totient function phi of n for any integer n? If I have an integer n, so the Eulers totient function is defined as number of positive integer less than n and relative prime to n. Now let's take a look at an example to illustrate this. Okay, so suppose I choose n equals, say, 10. Now what is the Eulers totient function phi of n for n? So that means in that case n equals 10, so phi of 10. So phi of 10, phi of 10. Phi of 10 is defined as the number of positive integer less than n. Okay. Which number, positive number, is less than n? N is 10. So the number which are less than n, numbers that are less than n are 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So these numbers are less than 10. Okay. Now, the Eulers totient function is defined as number of positive integers, 1 to 9, less than 10, and relatively prime to n, to 10. So then we need to compare which number is relatively prime to 10. Okay, so we need to check, the one way to do it is to check the greatest common divisor between this number and the 10, right? So we check 1 and 10, GCD of 2 and 10, and all the way to GCD of 9 and 10, right? Okay, so GCD 1 of 10, 1 and 10 is 1, so that means 1 and 10 is relatively prime. Now what about the GCD of 2 and 10? So the greatest common divisor between number 2 and 10 is 2. So that means they are not relatively prime, right? Excuse me. Now, what's the greatest common divisor between 3 and 10? So it's 1, right? Because the only divisor between 3 and 10 is 1. So 3 and 10 is relatively prime. Okay. Now 4 and 10. So 1 and 10, that's true. 2 and 10, no. 3 and 10, yes. 4 and 10, so they have a common divisor, which is 2. So they're not relatively prime. 5 and 10, of course, they're not relatively prime because they have a common factor 5, right? 6 and 10, no, because you can find a common factor 2. Now 7 and 10, the only divisor who can actually divide 7 and 10 is 1. So that means they are relatively prime. 8 and 10, no, they have a common factor 2. 9 and 10, yes. So we find 1, 2, 3, 4. 4 numbers, 4 positive integers less than 10 and the relative prime to 10. So we can say phi of 10 is 4. Okay, so we find out the phi of 10 by the definition of Euler's Tolte's function. Now let's take a look at another example. What is the phi of 12? Phi of 12. If we use the definition, then we need to check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? We have 11 numbers, and which we're going to compare each individual one with 12 to see whether they are relatively prime. 1 and 12, yes. 1 and any number are relatively prime because the common factor is 1. 2 and 12, no. 3 and 12, they have a common factor 3, right? So they're not relatively prime. 4 and 12, they have a common factor 4, so they are not relatively prime. So they also have a common factor 2, so they have more than one common factors other than 1 and itself. 5 and 12, yes, you cannot find any factor that are not a 1. Okay. 6 and 12, not, because 6 is a common factor. Okay, so they are not relatively prime. 7 and 12, they are relatively prime. 8 and 12, yes or no? No. 9 and 12, no, because they have a common factor 3, right? 10 and 12, so they have a common factor 2. So 11 and 12, yes. So I find a 1, 2, 3, 4. So that's also 4. What about the phi of 17? So you need to check each integer, positive integers less than 17, right? So you can check 1, 2, 3, 4, all the way to 16. So 1, 2, 3, all the way to 16. So they are a total of 16 numbers, right? So 1 and 17, yes, they are relatively prime. 2 and 17, yes, relatively prime. Actually, so all the numbers between 1 and 16 are relatively prime to 17. Why? Because the only divisors for 17 is 1 and 17, right? So any other numbers are not divisors of 17. So they're all relative prime to 17. So this is 16. Now what about 23? What about 35? Okay, I'm not going to work on this. But for 23, you will find out it's relatively easy to find the phi of 23. It's 22. Think about this. Why? So remember, in the previous slide, we showed that the phi of 17 is 16, right? And the phi of 23 is 22. Why? You will find out 16 is 1 less than 17. 22 is 1 less than 27 or 23. Why this is the case? Because in general, for any prime number p, phi of p is p minus 1. This is always true because if for a prime number p, so you cannot factor the p. So any number with positive number which is smaller than p is relative prime to p. So any number between 1 and p minus 1 is relative prime to p. So that means all the numbers, from 1 to p minus 1 are relative prime to p. So that means based on definition for Eulers Theorem function, phi of p is p minus 1. Now, the other property about Eulers Theorem function is very important. Suppose I have a p and a q, and p and q are two prime numbers. P is a prime number, q is a prime number, and the p and the q are not the same. Okay, then we can prove that the Eulers Theorem function phi of p times q is the same as phi of p times phi of q. Now, because p is a prime number, so it is p minus 1, and the q is a prime number, another prime number, so it's a q minus 1 based on the first property. This is a very important property because later on in the computer security, network security, we're going to use this one. Okay. Now, we talk about the Eulers Theorem function, and then we may ask a question. Why we want to introduce this function? Now, we will find out the Eulers Theorem function is a very interesting function because for any number, integers, the Eulers Theorem function is not really predictable. It's not going to generate the result that's predictable. Now, let's take a look at the values of Eulers Theorem function for the integer n, if n from 1, 2, 3, 4 all the way to 30. Okay, so now when n equals 1, the Eulers Theorem function phi of 1 is 1, and the phi of 2 is also 1, right? By definition. So the number of integers that are smaller than 2 and the relative prime to 2 is only 1. So there's only 1. So that's 1. Now, phi of 3 is 2. That's not surprising because 3 is a prime number. So phi of 3 is 3 minus 1. It's 2. Phi of 4. Let's see. Phi of 4. We just find 1, 2, 3 integers that are smaller than 4 and the relative prime to 4. So 1 is always the 1, the result. 2 is not, because 2 and 4 has a common factor, 2. So 2 and 4 are not relative prime. And 3 and 4, they are relative prime. So phi of 4 is 2. So only 1, 2. There's only 2 numbers. Phi of 5 is 4, because phi is a prime number. Phi of 6 is also 2. That's very interesting, right? Phi of 6. We need to compare 1, 2, 3, 4, 5. So 1 and 6 is relative prime. 2 and 6 is not relative prime. 3 and 6 is not relative prime. 4 and 6 are not relatively prime, so phi of 6 are relatively prime, so there's only 2. So that's 2. So here's a list. Now let's pick another example, 24. If we try to actually calculate a phi of 24 by definition, it's pretty tough, right? But it's doable. Now let's pick another example. Let's see. 26. Maybe 26 is an easy one to calculate. Now phi of 26. Now how can we do this? So by definition, we need to check 1, 2, 3, 4 all the way to 25 to see whether 1 is relative prime to 26. Yes. 2 is relative prime to 26. No. 3 is relative prime to 26. Yes. So we can always check each individual one from 1 to 25, right? But there's a better way. Remember, in the previous slide, we showed that if I can factor 26, I can factor 26 as 2 times 13, right? Now, 2 is a prime number, 13 is a prime number, so I know it's a phi of 2 times phi of 13, right? Now, what is phi of 2? It's 1. Okay. What is phi of 13? Because 13 is a prime number, so the phi of 13 is 13 minus 1, 12. So it's 12. So if we know certain of the property of the number, so we can factor the number into the product of two prime numbers, and then we can actually, calculate the Eulers-Tortius function very easily. Okay. Now 29 is 28 because 29 is a prime number, so it's a 29 minus 1. So you can actually check this, to see that table actually give you the Eulers-Tortius function for the numbers from 1 to 30. Now, the Eulers theorem is built upon the Fermat's theorem. So the Eulers theorem says for every A and N that are relatively prime, if A and N are relatively prime, then A to the phi of N and the 1 is congruent modulo N. So if I write in another way, it's basically say A to the phi of N mod N is 1. Okay. Or the alternative form, just like the Fermat theorem says, A to the phi of N plus 1 mod N is A. Now, Euler's theorem is the generalization of Fermat's theorem. Why? Because if N is a prime number, then we know phi of N is N minus 1, right? So if N is a prime number, the Euler's theorem becomes A to the, because phi of N is N minus 1, so it's A to the N minus 1 equals 1 mod N, if N is a prime number. That's exactly the Fermat theorem. So the Euler's theorem is actually the generalization of Fermat theorem. Okay, but Euler's theorem also apply to a general value N. So there's no actually precondition for N. So we don't assume N is a prime number. N could be any number, but then we replace N minus 1 with phi of N. So that's the Euler's theorem, which is generalization of the Fermat theorem. The Euler's theorem is very important. Okay, we will see that. Now, since prime number plays a very important role in number theory, so we need to find an algorithm to test the primarity of a number. Okay, so suppose I have a number n. How can I test whether n is a prime number or not? Okay. Now, first, we should exclude all the even numbers, right? Because even numbers are not prime number because they can be divided by 2. So they're not prime numbers. So now suppose n is an odd number. How can I test n is a prime number? Now traditional approaches basically are based on the definition of prime number. It's based on the definition of prime number. That means we divide n by any number smaller than n. You know, if none of these numbers can divide n, then n is a prime number. Okay, so on the right, we actually provide these pseudocode to test whether n is a prime number. So let's say we just do the loop for I from 2 to half of n. That's a floor division plus 1. Okay, so we just do the loop for I from 2 to half of n plus 1. Now, if n modulo I is 0, that means m divided by I, and then we get a remainder 0. So that means I divides n, right? If this is true, then I divides n. So that means n can be divided by I, which is smaller than n, so n is not a prime number. So we're going to return composite. Now, if for all the i's from 2 to half of n, none of this is true. So that means we never execute the if statement. Then we return prime. So that means that number n is a prime number. So this is a traditional approach. Now you think, oh, that's simple, right? But we need to realize that this program can only test n when n is a very small number. Okay, when I say small number, that means the n is less than probably like a 1 couple of billion or something. You know, it's not a huge number, because in network security, in the encryption algorithm, we're going to test the primarity of number which contains like a couple of hundred digitals. It's a very, very long number. Now in this case, the traditional approach never going to work. Okay. Now we can actually use the alternative approach. The alternative approach uses the statistical primarity tests. Okay. So this is based on the property of the prime numbers. Now for one for which all prime numbers satisfy properties, but some composite number also satisfy these property. So that means the statistical primarity testing basically, provide a result with certain confidence. Now, what does that mean? So that means if we want to use a statistical primarity test for number n, right? And then if we pass the testing, we can claim n is a prime number, and or we can say 99.99999% of chance n is a prime number. Okay, so that's a statistical primarity test. That means even past the test, even we pass the test for n, we still cannot, tell n is 100% prime number, but we can tell by 99.9999% of chance, which is very close to 100%, that the n is a prime number. Okay. Now let's discuss this primarity testing even further. We mentioned that we can use the traditional approach for a small number. Okay, so we can test whether the number is a prime number if the number is small. But for big number, we cannot use the traditional approach. We have to use the statistical primarity tests. Now, why? Let's take a look at the example. Okay, suppose I have a number n, n has 100 digits. N is an integer with 100 digits. Let's say right 9, 8, 7, 9, 2, 0, 4, 7, there's a whole much digital, and then we have 3, 7, 9, 1. Okay, now we have a total of 100 digits. Okay, I skip a middle because 100 digits is so long, so I cannot write all of this. Now, if we want to test whether n is a prime number, what we do? Then we use the traditional approach. You can say, okay, can we use the traditional approach? Now let's try it. Okay. Now, if n has 100 digits, then n is approximately 10 to the 100, right? For 10-digit number, the value for the n is approximately 10 to the 100. That's basically for 100 digits, an integer of 100 digits. So then, what does that mean? We need to do the for loop from 2 to half of this number. Okay, approximately half of this number. Now, what is the half of this number? So n divided by 2, right? So it's 5 times 10 to the 99. Okay, so that's the total of loops we need to perform. Okay, that's a total of loops we need to perform. Now, suppose I have a CPU which can perform 10 billion for loops per second or per second. Okay, I can perform 10 billion loops per second. That's my CPU. Okay, now the total number of loops I need to perform is 5 times 10 to the 99. So now how much time do I need to complete that loop? Now, of course, that loop is, half of this number n is the worst scenario. If for certain number I, which can divide n, so that means n mod I equals 0. That means n divided by I, and the remainder is 0. So that means I divides n. Then I stop the algorithm. I return composite, right? Now, if none of the I can divide n, so then in that case, I have to go all the way from 2 to half of n. So I have to actually complete the whole loop. That's the worst scenario. And then if none of this can divide n, then I can return prime. So let's say, suppose actually n is a prime number, so I need to complete the whole loop. Okay. Now, that's the total number of loop I need to perform. Now, that's the total number of loop. 10 billion is the number of loop I can perform in 1 second. So what is 10 billion? 10 billion is actually 10 to the 10. Because 10 billion is actually can write as 10 billion can be write as 10, 0, 0, 0, 0, 0, 0, 0, 0, 0. So that's 1,000, million, billion, and 10 billion. So we have total how many zeros? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 0. So 10 to the 10. So that's the total number of loops I need to perform. That's the total number of loops I can perform in a second. So this gives you the total number of right? So with the CPU we have, which can perform 10 million for loops per second. So to finish that many loops, I need 5 times the 10 to the 89 seconds. Now let's convert this into year, okay? So convert 5 times 10 to the 89 seconds into a year, I need to divide these seconds by 60. That gave you minutes, right? The number of minutes. And then divide 60 again, that gave you a number of hours. And then the number of hours divided by 24, that gave you a number of days. And for then divided 360, that's the number of days in a year. So this gave you the total number of years I need to take to complete this for loop. What does this tell you? Now, I just need a ballpark estimate, so I can actually just increase the denominator. I keep the numerator 5 times 10 to the 89, but I increase the denominator 60. I change to 100. So the denominator is bigger, then the whole number is smaller, right? I increase the denominator, and I actually convert 60 to 100, 24 to 100, 360 I replace with 1000. So definitely this number is smaller than this. Now what is this, the result? 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 zeros. So that's a 10 to the 9. 5 times 10 to the 89. So this gave you 5 times 10 to the 80 years. So I need more than 5 times the 10 to the 80 years. Do you have any idea what does that mean? What's the, what's life of a universe? The Big Bang, based on Big Bang theory, the Big Bang actually started at 14 billion years ago. So that means our universe actually started 14 billion years ago. Okay, 14 billion is actually, it's actually 1.4 times the 10 to the 10, right? That's 14 billion. Now that algorithm requires more than 5 times the 10 to the 80. Much bigger than 10 to the 10. So this basically, it's an impossible job, because try to test whether n is a prime number, we need more than that many years. Okay, so that's the reason why we need to actually figure out another way to test the primality of a number. If the number is big, like a 100 digits number. Now, in modern encryption algorithm, we actually need a number which contains 200 or 300 digits, way bigger than this 100 digits number. Now, how can we deal with that? So we use the statistical primality tests. So one of the statistical primality test algorithm is called Miller-Rabin algorithm. Now the test is based on the Fermat theorem. Okay, so here's the pseudocode for the Miller-Rabin algorithm. Okay, so suppose we're given an integer n, right? Then n should be an odd number, because if n is an even number, then we stop the test, because n is not a prime number. Now, suppose n is an odd number, and a huge number, then what should we do? Now, the first thing we need to do is, if n is an even number, then n minus 1, so n is n is an odd number. So that means n minus 1 is even number, right? So if it's an even number, then we can find the factor 2, right? If n minus 1 is an even number, so 2 is a factor. So let's assume that we can write n minus 1 into the form like 2 to the k times some q, and the q is odd. That's doable, right? If q is even, then we can actually factor the q even further, and then we eventually can always write n minus 1 in the form like 2 to the k times q. Okay, so this is actually the first step. So for any odd number n, we just factor the n minus 1. So the n minus 1 going to look like this. So let's take an example. When I use an example, I always use a small number, okay? But this also applies to the big number. And the algorithm always, used it to test a bigger number. So let's say n is, let's say 97, right? So what is n minus 1? N minus 1 is 96. So let's say, how can I write 96 in terms of this format? So 96 divided by 2. Okay, so it's a 2 times 48. So I can still, continue to extra factor 48. So I got 2 squared times 24, right? And then I can go even further, 2 cubed times 12, right? So 24 can be written as 2 times 12. So, and then there's another, this is still an even number, so I can write 2 to the 4th times 6. So I can even write a 2 to the 5th times 3. Okay, now I got the 4. So now in this case, I can write n minus 1 in terms of 2 to the 5 times 3. So in this case, k is 5, q is 3, right? I can always write any odd number n and the factor n minus 1 into this format. Okay, so that's the first step. And then in the test, we're going to select a random integer a. A random integer. Now a is between 1 and n minus 1. That's a huge range, right? N is a huge number, then a can be selected from 1, 2, 3, 4, all the way to n minus 1. Okay, now we're going to do the testing using mirror robin. Now, for any random selected integer a, now if a to the q mod n is 1, a to the q mod n is 1, then we can say n is probably a prime. I say maybe a prime. And we return. The tester going to return, say, maybe a prime. Now, if a to the q mod n, is not equal 1, it's not that this is not true, then we actually switch to the for loop. And the for loop, we're going to go the loop from 0 to k minus 1. Remember, what is k? K is the power of 2. Okay, so in this case, when I choose n equals 97, then k is 5, right? So I do the loop from 0 to 5 minus 1, which is 4 in this case. And then you test this again. So this, read this very carefully. So if a to the j, so that's 2 to the j is a power, times q. Okay, so that's the power of a. So a to the 2 to the j times q mod n is n minus 1. Then we return maybe a prime. Okay, for each j. So we start from j equals 0, and if this is true for any of the j between 0 and the k minus 1, then we return maybe prime. If none of the j satisfy this condition, then once we complete the for loop and none of this is true, then we complete the loop, for loop, and then we just say return composite. Okay, so if this is not true, if none of this is true for this is not true for any j, then we claim that the n is not a prime. But if one of this condition is true, then we cannot say n is a prime, but we can say n is probably a prime. We still cannot exclude that the n is a prime. So, okay, that's a mirror robin. And then you may ask, what's the point of this mirror robin? Now let's take a look at the next slide. Because every time when I test the n, when I do the test n, if the test returns maybe prime, so I cannot exclude, this is a prime. So it's the only thing I can say is this is probably there's still a chance that this is a prime. Okay, the next slide I'm going to tell you, every time when a test of n is successful for an integer a, that means the chance that this n is a prime increases. Okay, let's just go to the next slide. Now, in previous slide, we know that if we use the mirror robin algorithm to test the primarity of an integer n, so we're going to use a randomly generated value a, an integer a. So a is between 1 and n minus 1, right? So we can test whether the condition a satisfies certain, modulo condition. Okay, if none of the conditions is true, then the mirror robin returns composite. If mirror robin returns composite, that means n is not a prime. Now the other possible return value is maybe a prime. So mirror robin may return, maybe a prime. So now you may think, still mirror robin cannot say it's a prime number. It's just say maybe a prime. What's the point of this? Now let's look at it further. Okay. So every time when mirror robin algorithm returns maybe a prime, that means, it's probably a prime. But there's still a chance that it's not a prime, right? However, here's the most important part. Now, each time when mirror robin returns maybe a prime, not a composite, so that means the probability that n is not a prime after one test is 1/4. So that means when mirror robin return maybe a prime result, then the probability that the n is not a prime is 1/4. That's about 25%. So I can say the probability that the n is not a prime is only 25%. Or in other words, the probability that the n is a prime number is 75%. Okay, that's a big probability. But you can still say there's still a chance, like a 25% of chance that the n is not a prime, right? What's the point of this? So n is not, I cannot say n is a prime. There's still a 25% chance n is not a prime, right? However, the beauty of the mirror robin algorithm is that we can actually use the mirror robin test multiple times. Okay, so if we actually test once, we can say n is not a prime. The probability that the n is not a prime is 25%. Now, how about if we repeat the test? And in the second test, Miller-Robbins still return maybe a prime. And then we try third test and the fourth test. We continue to apply the Miller-Robbins test. If all the tests return maybe prime, then we find out the probability that the n is not a prime after, let's say, t tests is only 1/4 to the t. So that means each time, when the Miller-Robbins passes that returns that maybe a prime, then the chance that the n is not a prime becomes smaller and smaller. So that means the probability that the n is not a prime after t test, you apply the Miller-Robbins t times. Each time you randomly pick a different a, then the chance that the n is not a prime is only 1/4 of the t. What does that mean? So if I actually use the Miller-Robbins 10 times, let's say t equals 10, I test it 10 times. So the chance that the n is not a prime after 10 tests is 1/4 to the 10. So in another word, the probability that the n is not a prime after t test is 1/4 to t. Now, then, in another word, the probability that the n is a prime after t test is 1 minus 1/4 of the 10. Then this gave you like a 0.9999. So now you can say, after actually 10 tests using the Miller-Robbins, the chance that the n is a prime number is 99.9999%. That's a very, very close to 100%. Okay. Now, if you still say, oh, it's still not 100%, I cannot say 100% that the n is a prime number, then you can increase the number of tests. From t equals 10, I can test 20 times. If all 20 tests pass, okay, if I pass all the 20 tests, then I can say that the n is a prime after 20 tests is 1 minus 1 to the 4th to the 20. Now this one, that's almost 0. So that means the probability that the n is a prime after 20 tests is very, very close to 100% chance. Okay. Now, so this is basically the one we use to test the primality of a random number n. Now, even though the chance is small, but there's still a chance that the n may not be a prime, right? But the interesting thing is, if I use Miller-Robbins and I pass like 20, 30, or 90 tests, okay, then all actually successful, then I can claim that the n is most likely a prime number. Now, even if it's not a prime number, then that composite number is very close to the prime number. It's almost same as a prime number. You can use as a prime number. That's the beauty of Miller-Robbins test. So in next module, we're going to talk about how to apply these primality tests and in the network security, in the encryption and decryption algorithm. Thank you.